Good evening and welcome back to this quiet corner of the night sky. Tonight, we're traveling to a planet that never quite learned to stand straight. Out beyond Saturn, past the brighter giants most people picture first, Uranus moves through darkness in a strangely restful way. While the other major planets spin more or less upright, Uranus turns as though it has been gently laid over. It is tipped by about 98 degrees, so far that its poles point sideways through much of its year. That number can sound tidy on paper, but the reality of it is wonderfully odd. In a system that usually prefers order, Uranus feels like one beautiful exception. I think that is part of why people remember it, even if they know little else. Tonight, we'll stay with that exception and let its mystery unfold slowly. And for now, there is nothing you need to solve, only a distant world to keep you company. If these long, quiet journeys through space have become part of your evenings, a like or subscribe truly helps. It lets this little channel find other listeners who enjoy calm science told at an unhurried pace. Thank you for spending your time here with me tonight. For the next while, though, you can set the day down completely. Let your jaw unclench a little and let your breathing become easier without forcing it. Let the room grow softer around you as your attention drifts outward. We are going very far away, to a pale world where even the sunlight arrives thin and gentle. It is a good place for a quiet question. What happened to Uranus so long ago that no other major planet seems to share? That question has waited billions of years, so it can wait for us to approach it slowly. Most planets in the solar system behave like spinning tops crossing a tabletop. They lean a little, certainly, but they still keep a clear sense of up and down. Earth, for example, tilts by about 23.5 degrees, and that modest slant gives us seasons. Mars leans by nearly the same amount, which makes its year feel somewhat familiar in principle. Saturn and Neptune tip a bit more than Earth does, but both still remain broadly upright. Jupiter barely tilts at all, as though it prefers steadiness over drama. Then there is Uranus, which goes almost all the way over and a little beyond. When I picture the planets together, Uranus always feels like the one reclining at a formal dinner. It does not just lean farther than the others, it breaks the pattern almost completely. That broken pattern is the beginning of everything strange about this world. Because Uranus has tipped slightly past a right angle, astronomers count its rotation as backward relative to most neighboring planets. In that technical sense, it spins the opposite way from the majority of the solar system. Venus also rotates backward, though for reasons believed to be entirely different. Still, the bookkeeping matters less than the image itself. Uranus does not seem to twirl upright as it circles the Sun. It rolls, or at least appears to, carrying its sideways axis around its long path. That image has always felt oddly peaceful to me, like a globe drifting on its shoulder. The violence, if violence caused it, belongs to a time unimaginably far behind us. What remains now is a calm, blue-green planet moving without complaint through the cold. Its present quietness makes the old mystery feel even deeper. Nearly every unusual thing about Uranus can be traced back to that single tipped axis. Its bizarre seasons come from it, and so does the arrangement of its rings and moons. Even one of the planet's great internal puzzles may connect back to the same ancient event. To understand why Uranus lies on its side is, in a real way, to understand Uranus itself. That is why this question has such a long reach. It is not one isolated curiosity tucked away in a textbook margin. It is the key that seems to fit many locks at once. I always like when astronomy offers a single fact that quietly rearranges everything around it. Uranus gives us exactly that kind of fact. Once you see the tilt clearly, the whole planet begins to make a different kind of sense. Uranus belongs to the pair astronomers call the ice giants, along with Neptune. It is much larger than Earth, holding roughly 14.5 times our planet's mass. In size and substance, it stands between the rocky inner worlds and the larger gas giants, Jupiter and Saturn. Its bulk is made largely of materials astronomers loosely call ices, including water, ammonia, and methane. Those substances are not kitchen ice there, of course, but exotic forms under tremendous pressure. Around that deep interior lies a thick atmosphere of hydrogen and helium. There is no solid surface waiting beneath the clouds for anyone to step onto. I find that detail wonderfully disorienting, a reminder that some worlds are places only in the loosest human sense. Uranus is less a landscape than a layered sphere of fluid, haze, pressure, and cold. It also holds an important place in the history of discovery. The planets out to Saturn were known in antiquity because they shine brightly enough for the unaided eye. Uranus sits near the edge of naked eye visibility, faint enough to be mistaken for an ordinary star. It was only recognized as a planet after the telescope entered human life. In that sense, Uranus was the first truly new planet added to the solar system. It widened the known map of the Sun's family beyond the old classical boundary. I like that its posture is unusual, and its discovery was unusual too. Even its entrance into our awareness carried a kind of sideways quality. For a while, though, its strangest trait remained hidden. A distant, pale disk does not easily reveal the angle at which it spins. The favored explanation for that angle is dramatic, though the planet itself no longer looks dramatic at all. Most researchers think Uranus was struck very early by a massive body, perhaps several times Earth's mass. Not a direct hit, but an off-center collision capable of knocking an entire world nearly over. In the crowded youth of the solar system, such encounters were far more possible than they are now. If that happened, the blow would have changed the planet's posture for the rest of time. Yet quieter ideas still remain on the table. Some scientists have wondered about a lost moon, or a long gravitational tug acting over ages. I appreciate that the best answer can still leave room for humility. Uranus may have been toppled by catastrophe, or persuaded sideways by patience. Either way, the question is not fully closed. That uncertainty is part of what makes this planet so compelling. We know the tilt is real, and we know it is extraordinary among the major planets. We know the leading explanation is an ancient giant collision near the beginning of planetary history. We also know that science is most honest when it leaves a door open for better evidence. Uranus has not given us a signed confession, only clues written in posture and motion. There is something deeply satisfying about a mystery that remains disciplined instead of sensational. Not every unanswered question needs to become a spectacle. Some can simply rest in the dark, waiting for us to look more carefully. Uranus is one of those mysteries. The farther away a world is, the more gently it seems to ask for patience. So tonight, we begin with a planet that lies down where all the others mostly stand. We begin with a blue-green ice giant, about 14.5 Earth masses, discovered by telescope rather than by ancient stargazers. We begin with a tilt of about 98 degrees, a backward spin, and a puzzle old as the solar system. We begin, too, with the possibility that one ancient impact changed everything that followed. And we keep beside it the quieter alternatives that have not entirely faded away. From here, the next question comes naturally and almost softly. How do astronomers know Uranus is tilted so extremely in the first place? A planet that distant does not give away much at a glance. So in the next stretch of our journey, we'll look at how its posture was patiently read. And as we do, the sideways world will start to reveal itself a little more. And that patient reading begins with admitting how little Uranus offers anyone looking quickly through a telescope from Earth. From a distance, it appears as a small, pale blue-green disk with almost no obvious markings at all. Jupiter advertises itself with bands and storms, and Saturn with belts, contrasts, and a ring system impossible to ignore. Uranus is quieter than that, almost shy, as though it prefers being mistaken for something simpler than itself. For a long time, that smooth appearance made even the basic question of its rotation surprisingly difficult to answer. Astronomers usually track a planet's spin by watching clouds, spots, or streaks travel steadily across the visible face. On Uranus, there were hardly any features bold enough to follow with confidence from one night to another. A world that keeps such a blank expression does not easily reveal where its poles are pointing. I have always liked that about it, because some truths in astronomy arrive only after stubborn gentleness. So the discovery of Uranus's posture did not come from one dramatic photograph, but from many careful clues. Even the planet's day had to be teased out indirectly before its sideways nature could be understood with confidence. Once measurements improved, Uranus was found to complete one rotation in about 17 hours, give or take. That is not especially slow for a giant planet, though its motion is counted backward by astronomical convention. Still, knowing the length of a day is not the same as knowing how the axis is tilted. A spinning globe can turn quickly or slowly and still keep its poles in many different orientations. The bland disk alone could not tell observers whether Uranus stood mostly upright or leaned nearly flat. That distinction required geometry, patience, and objects around the planet that were easier to interpret than clouds. In a way, Uranus had to be read by its companions, which feels appropriately indirect for this world. The planet itself stayed nearly expressionless, while the surrounding system quietly gave away the larger truth. So astronomers looked outward from the globe to the things moving faithfully around it. Those companions matter because moons and rings usually orbit close to a planet's equator rather than randomly. That pattern appears again and again across the solar system, and it follows naturally from how systems form. A spinning planet gathers material into a flattened arrangement, and nearby satellites tend to inherit that same plane. Jupiter's major moons stay near its equatorial region, and Saturn's bright rings do the same beautifully. If you can determine the plane in which a planet's moons travel, you can infer the equator. And once the equator is known, the tilt of the spin axis follows from simple celestial geometry. This is one of those elegant astronomical shortcuts that feels almost like listening to echoes in a canyon. You may not see the hidden shape directly, but the returning sound tells you what the walls are doing. Uranus obeys this same rule as faithfully as any other major planet in the Sun's family. Its moons and rings circle where its equator is, and that fact became the key to everything. What made the result so startling was that Uranus's equator turned out to be tipped almost completely sideways. Its moons were not moving around a comfortably upright world with a modest lean like Earth or Mars. They were circling a planet whose equatorial plane was itself tilted nearly on end relative to its orbit. That means the whole system shares the planet's posture, as though the household reclines with the house. The rings follow that same slanted plane, and so do the regular moons nearest the planet. Instead of tracing a belt around a standing globe, they sweep around something lying almost flat. If the planet's equator is sideways, then its axis must be sideways too, because one defines the other. That conclusion did not depend on imagination or storytelling, only on repeated measurements agreeing over time. I find that satisfying because the strangest facts often arrive wearing the plainest mathematical clothes. Uranus was not guessed to be unusual. It was shown to be unusual by the motion around it. From Earth, this tilted arrangement creates views that no upright giant planet can imitate in quite the same way. During some long stretches of Uranus's 84-year orbit, we look more or less down onto the Moon system. When that happens, the moons appear to trace nested circles around the planet like a target or dartboard. Each orbit sits inside another, centered on the pale disk, neat and almost decorative from our distant perspective. That pattern is a giveaway, because an ordinary upright planet would not present its satellites this way. Seen from the side, most moon systems look more like a line strung across the planet's middle. Uranus instead sometimes opens its system toward us, revealing those circular tracks almost face-on through space. The image is so tidy that it hardly looks real at first, more diagram than sky. But the sky is often better organized than our first intuitions, which is one reason astronomy stays humbling. Those open views became one of the clearest visual signatures that Uranus was tipped far beyond the usual range. At other times, the same system closes up and presents the opposite geometry to observers watching from far away. The circles flatten into a narrow line when the ring plane turns edge-on to our line of sight. Moons that once seemed spread around a target now appear compressed along a single slender track. The rings do the same, becoming so thin in profile that they can nearly disappear from view. Over decades, as Uranus advances along its long orbit, The presentation slowly shifts between these two extremes. Open, then closed, then open again, all at a pace that asks human observers to think in generations. That slowness is part of the lesson, I think, because some planetary facts unfold too gradually for impatience. No one night tells the story by itself, but many years layered together begin to reveal the pattern. The changing view was not a curiosity on the side, it was evidence written directly into perspective. By watching that perspective evolve, astronomers could read the angle of the planet's entire rotational frame. The rings confirmed the same story, and they were discovered in a wonderfully understated way, befitting Uranus itself. These are not broad, glowing bands like Saturn's, but narrow, dark rings made from dim material. They reflect little sunlight and were easy to miss when observers searched for something bright and obvious. Their discovery came instead through stellar occultation, a phrase that sounds technical but describes something beautifully simple. A distant star was being watched as Uranus moved in front of it from our viewpoint. Before the planet itself covered the starlight blinked out briefly several separate times. After Uranus passed across, the same pattern happened again in reverse, like footsteps entering and leaving snow. Each disappearance marked one narrow ring, crossing the line between Earth and the distant star. I love that method because it feels less like seeing and more like noticing interruptions in silence. From those repeated blinks, astronomers could map the rings and determine how their plane was tilted. And that plane matched the moon's, which matched the equator, which matched the idea of a sideways planet. No single observation had to carry the entire burden because the pieces reinforced one another so cleanly. The moons traveled in the same slanted arrangement as the rings, and both stayed tied to Uranus. Again and again, the system pointed to the same conclusion from different directions and by different methods. That is usually how confidence grows in astronomy, not through spectacle, but through agreement among patient measurements. A faint ring edge, a moon's path, a changing viewing angle, a blinking star far beyond. Each clue by itself might feel modest, but together they become something stronger than any dramatic first impression. Uranus did not announce its posture with color or weather, or a bold visible axis across its face. It had to be understood by accumulation, which is a very gentle way for truth to arrive. The sideways world revealed itself slowly, through small consistencies that became impossible to ignore. There is something almost meditative about learning a planet this way, sign by sign across many quiet years. Astronomy often works through fragments gathered patiently, especially when the object under study refuses theatrical behavior. You watch a moon return, then another, then a ring vanish, then reappear, and eventually a structure emerges. Not because the universe suddenly became clearer, but because your record of it became longer and better. I think that process is one reason the subject feels so restful when approached without hurry. It rewards attention more than urgency, and Uranus may be the perfect example of that temperament. Its tilt was not snatched from the sky in one triumphant instant by a single decisive observer. It was assembled carefully from geometry, repetition, and the willingness to trust faint evidence over time. By the end, the conclusion was firm. Uranus is not standing like its neighbors at all. It is lying on its side, and its moons and rings have organized themselves completely around that fact. But knowing how astronomers measured the posture is not the same as understanding what that posture does. Once a planet is tipped almost flat, light and darkness begin behaving there in deeply unfamiliar ways. The axis is no longer just a number in a table or a strange diagram in a book. It becomes a governing force, shaping seasons, weather, and even the meaning of day across that distant world. A planet that lies down under the sun cannot live by ordinary rhythms for very long. That is where the mystery becomes more than geometry and starts becoming a way of life. The evidence from moons and rings tells us Uranus is sideways with remarkable confidence and precision today. What it does not tell us, at least not yet, is how that sideways stance transforms an entire year. To understand that, we have to follow sunlight across a world that receives it at impossible angles. And once we do, Uranus stops being merely unusual and starts feeling unlike anywhere else in the solar system. And once we do, sunlight on Uranus begins to behave less like weather and more like choreography from elsewhere entirely. The planet needs about 84 Earth years to complete a single trip around the Sun, moving slowly outward. That means one Uranian year lasts longer than many human lives, which already makes the place feel strangely patient. On a world tilted modestly, such a long year would still preserve familiar rhythms of dawn, noon, evening and night. But Uranus carries its axis so far sideways that the Sun reaches it from angles no upright planet endures. For long stretches, one pole leans almost directly towards sunlight, while the opposite pole faces outward into deep darkness. The geometry sounds abstract until you imagine a globe resting nearly flat, with daylight pouring sideways across its surface. I always find that image quietly unsettling, like seeing seasons rewritten by someone who never visited Earth at all. On Uranus, the tilt is not a background detail tucked behind the climate, but the climate's central organizer. Everything about the year begins with that sideways posture and unfolds from it with a kind of alien calm. Because the orbit is so long, those polar seasons do not pass quickly the way winter and summer do here. Each pole spends roughly 42 years in continuous daylight, followed by another 42 years without sunrise. At the summer pole, the sun does not climb and descend as ours does through ordinary days and months. Instead, it circles and circles, always present, tracing slow loops in the sky without ever truly leaving. At the winter pole, there is no morning to wait for and no sunset to remember afterward. Darkness simply remains, not dramatically but steadily, as though the sky has forgotten another possibility for decades. That length of uninterrupted light or darkness is difficult to picture because our instincts expect change every day. Even the most stubborn Arctic season on Earth still feels temporary compared with half a lifetime under one condition. Uranus stretches one season so far that it stops feeling seasonal and becomes almost like a separate world. It is one of those astronomical facts that sounds impossible until you realize the math leaves no gentler alternative. The planet does not spend its entire year locked into that extreme arrangement though, and this matters a great deal. As Uranus moves onward, it eventually reaches equinox, when the sun shines more directly over the equatorial regions. During that interval, the sideways geometry briefly becomes less severe, and the whole globe shares sunlight more evenly. Then the planet's actual rotation, about 17 hours for one full turn, becomes easier to recognize as daytime. Light and darkness begin taking turns across much of the world in a pattern that feels almost familiar again. Sunrise returns, sunset returns, and the rapid spin starts carving the globe into alternating hours of brightness and shadow. I like that temporary return to normality because it feels like the planet remembering another possible way to live. But the familiarity is only borrowed and only partial, because the long orbit soon carries Uranus back outward. The brief season of ordinary-looking days gives way again to the grander arrangement of poleward light and darkness. One hemisphere slowly inherits the sun, while the other slips away from it, and the decades trade places. That means the idea of a day on Uranus depends heavily on where you are and when you ask. Near equinox, a day behaves in the usual educational sense. Rotation brings daylight, then night, then daylight again. Near solstice, especially close to a pole, the same 17-hour spin no longer creates sunrise or sunset there. The planet keeps turning faithfully, but the sun simply circles overhead without dipping below the horizon at all. Or else it never appears, leaving the sky unchanged by rotation in any practical human sense whatsoever there. So Uranus preserves one steady rotational period while producing very different lived experiences of time across its surface. That kind of mismatch fascinates me because it separates clock time from sky time in a beautifully unsettling way. A stopwatch would say the planet spins quickly, yet a polar observer might experience one brightness for decades. On Earth, rotation and daylight feel tightly linked, almost inseparable, but Uranus quietly pulls those ideas apart. Its sideways stance edits the meaning of morning itself, which is a surprisingly intimate consequence of celestial geometry. You might expect such uneven illumination to create savage temperature contrasts between the bright pole and the dark one. If sunlight falls for decades on one end while the other waits in shadow, the difference seems obvious. And yet Uranus refuses that simple expectation, which is one reason the planet keeps rewarding patient second looks. Measurements show that temperatures near the cloud tops remain surprisingly even from equator to pole across the planet. The sunlit regions are not dramatically warmer than the darker ones in the way simple intuition would predict. Somehow, the atmosphere appears able to move heat around efficiently enough to smooth out those lopsided inputs. Warmth absorbed on the brighter side does not stay neatly where sunlight first delivered it to the air. Instead, circulation seems to carry energy across the globe, softening what should have become a harsher imbalance. I think that hidden balancing act makes Uranus feel less inert than its quiet face first suggests. A world can look still and yet be doing subtle, elegant work underneath, like a lake hiding strong currents. Exactly how Uranus manages that thermal balancing remains less settled than the measurements showing the balance itself today. The broad idea is atmospheric transport, with winds and circulation redistributing energy between long-lit and long-dark regions. But the details are not fully pinned down, especially on a planet whose interior seems stingy with escaping heat. That missing internal warmth makes the atmospheric puzzle even more interesting, because less extra energy is available overall. You might think a colder, quieter giant would struggle to keep temperatures so remarkably level from place to place. Instead, Uranus seems to compensate with an efficiency that still leaves room for real scientific uncertainty. I appreciate mysteries like that because they are not sensational. They are precise gaps inside otherwise solid understanding. We know the pattern is real and we have a plausible mechanism, but the full account stays unfinished. That unfinished edge gives the planet a little more depth, like a sentence whose final clause remains unwritten. Even here, where the facts feel serene, Uranus keeps one hand closed around part of the explanation. Its weather follows the seasons too, and the story there is gentler than the giant storms of Jupiter. The only spacecraft ever to pass close by arrived near solstice, when one pole faced sunlight most directly. At that time, much of the planet was locked into its long, bright summer or long winter night. What the spacecraft saw was a mostly smooth world, pale, quiet, and nearly blank to the eye. For years afterward, that image shaped the reputation of Uranus as the sleepy giant no one remembered fondly. I understand why, because a calm blue sphere with almost no features does look like astronomy whispering. But the stillness turned out to be partly seasonal, not proof that the planet lacked weather altogether. We had visited during one of the least revealing moments in its long cycle of changing illumination. The portrait was real, but it was incomplete, like judging an entire ocean from one windless afternoon. Uranus was not empty of activity. We had simply arrived when much of that activity was resting. Later, as the planet moved closer to equinox, telescopes began catching a livelier atmosphere than before. Brighter clouds appeared high in the cold air, and faint banding became easier to see across the disk. Observers even recorded a dark spot, the kind of feature associated with deeper weather systems on giant planets. That change did not mean Uranus had suddenly awakened from geological sleep after centuries of quiet behavior. It meant the changing angle of sunlight was altering the atmospheric response in ways the flyby never captured. Seasonal lighting appears to matter enormously here, perhaps stirring circulation differently when both hemispheres receive illumination again. I like the phrase, "we caught it sleeping," because it feels accurate without making the science theatrical. The spacecraft met one version of Uranus, and later observers met another version shaped by another season. Both were true, but only together do they show a planet more active than its first impression suggested. The sideways world keeps changing character as the sun shifts position around it over decades of patient time. All of this means the tilt is not merely something you sketch on a classroom diagram beside the orbit. It reaches into the lived rhythm of the planet and organizes light, weather, and even expectation itself there. The 42-year stretches of brightness and darkness come directly from that ancient sideways orientation in space. The brief return of ordinary day and night near equinox comes from the same geometry and nowhere else. The surprisingly even temperatures appear tied to how the atmosphere responds to this strange distribution of sunlight. And the weather seems to wake and quiet itself according to the same slow seasonal turning of years. That unity is one reason I find Uranus so satisfying as a subject for quiet thought at night. One tilted axis does not create one oddity. It creates a whole style of planetary existence outward there. The world becomes coherent in its strangeness once you stop treating the tilt like an isolated number. It is less a curiosity than a master key, opening several doors at once with one sideways turn. Yet describing what the tilt does only sharpens the more difficult question waiting behind all these consequences now. A planet can live beautifully with an extreme posture and still leave us wondering how it acquired it. Worlds are not usually born lying almost flat relative to the plane from which they formed around stars. Something had to intervene, either suddenly or gradually, to redirect a planet this massive so dramatically in space. That is where the story stops being seasonal and becomes historical, reaching back into the system's earliest violence. The long polar summers, the unusual days, and the shifting weather are effects, not first causes themselves. I think this is where Uranus becomes most haunting, because its calm present points toward a turbulent origin. The planet looks serene now, but serenity can be the final shape left behind by something enormous. To understand why sunlight behaves so strangely there, we have to ask what changed the whole world first. And once that question is asked plainly, it becomes very hard to look away from it. That question leads straight back into the solar system's earliest unrest, when young planets still shared space with unfinished worlds. Planets are generally born from a broad spinning disk of gas, dust, ice, and rock around a newborn star. Because that disk turns mostly one way, the worlds forming inside it usually inherit roughly similar, fairly upright spin directions. That shared alignment is why the major planets, despite their differences, mostly resemble tops leaning only a little sideways. So when one planet ends up nearly flat, something probably changed it after birth rather than during ordinary formation. Uranus looks less like a natural variation and more like a record of interruption written into planetary posture. The leading explanation is simple in outline, even if the details remain debated after years of careful study. Very early on, Uranus was likely struck by a large protoplanet, meaning a young world still growing itself. That impact would not need to hit head-on to matter, and in fact an off-center strike works better. A glancing blow can redirect a planet's spin without destroying it, which makes the idea surprisingly plausible. To understand why the impactor had to be so large, it helps to define angular momentum in plain language. Angular momentum is basically the persistence of spin, a planet's stubborn tendency to keep turning the way started. Anyone who has watched a spinning bicycle wheel resist being twisted has seen a small everyday version already. A world as massive as Uranus carries an enormous amount of that rotational persistence simply by existing and turning. Changing its orientation by nearly 90 degrees would require a tremendous outside push delivered in a new direction. A small object could scar the atmosphere perhaps, but it would never meaningfully lay the whole planet over. Uranus contains about 14.5 Earth masses, and that much bulk does not respond to pebbles. The object that struck it was probably one to several Earth masses, large enough to count as planetary. In the young solar system, bodies of that size were more common than they are in today's quieter arrangement. I find that era strangely vivid, like a construction site after dark, where unfinished giants still crossed paths. Computer simulations give this collision idea much of its strength because they can recreate something close to reality. When researchers model a large off-center impact into a young Uranus, the final tilt can approach 98 degrees. That matters because the number is not merely dramatic. It is the actual angle astronomers measure today. The models suggest that a properly aimed collision can transfer enough spin to reorient the planet almost completely. In that sense, the impact explanation is not just a story we like, but one physics can support. Still, there is an important complication, and this is where the picture becomes more careful than popular versions. One giant impact is efficient at tipping a planet, but it also tends to dump immense energy inside. It can spin the planet up strongly and leave it hotter, faster, and more disturbed than Uranus seems. Because of that, some scientists prefer two or more smaller impacts whose combined effects could build similar tilt. The broad idea remains collision either way, though the solar system may have used one hammer or several. The Moon system provides one of the most revealing tests of what happened because orbits preserve old geometry. If Uranus had already possessed its regular moons before the planet was tipped, a problem would appear immediately. Those moons would keep circling in the old plane they already occupied, not obediently follow the new equator. A planet can change its spin axis quickly, but distant satellites do not simply swing over in response. So after a late tipping event, we would expect a mismatched system with moons orbiting at awkward angles. Instead, Uranus's major moons travel in neat, nearly circular paths, closely aligned with the planet's tilted equator. At first glance, that order might seem to argue against any violent history, which is an understandable reaction. But in practice, the tidiness may be exactly what a major impact would leave behind after enough time. The key is that the collision would not only tip Uranus, it would also create a great debris disk. And that disk changes the whole story from one of disorder into one of slow rebuilding afterward. A large impact would blast rock, ice, and vaporized material into orbit around the newly tilted planet itself. Gravity would keep much of that debris from escaping, so over time it would spread into a flattened disk. Because Uranus's spin had already been redirected, the debris disk would settle around the planet's new equator. That means any moons forming later from that material would naturally inherit the tilted orbital plane we observe. They would not be older companions dragged along somehow, but younger worlds assembled after the reorientation happened. Small fragments would collide, merge, and gradually build larger bodies, the usual patient arithmetic of planetary systems. I like that image because it turns catastrophe into architecture without pretending the original blow was gentle. The same event that knocked the planet sideways may also have provided the raw material for its companions. So the orderly moon system is not necessarily evidence against impact, but possibly one of its clearest fingerprints. What looks calm today may be the polished end state of a long settling process that began violently. There is room for variation inside that picture, and researchers do not all favor the exact same sequence. Some models suggest pre-existing moons could also have been affected if Uranus still had surrounding disk material. In that case, gas and debris around the planet might have been pulled toward the new equatorial plane. Moons growing inside that disk would then migrate with it, ending up aligned without having formed entirely afterward. Either way, the central requirement is similar. Some substantial disk must have responded to the changed planetary spin. That disk, whether mostly impact debris or leftover building material, would help organize the regular moon family. The farther, smaller, more irregular moons do not challenge this very much, because they may have been captured. Most giant planets keep two populations anyway, a tidy inner family and a looser outer crowd acquired later. What matters most is that Uranus's main moons agree beautifully with the tilted equator, and agreement carries history. Their orbits feel almost like handwriting, neat lines left behind by events no telescope could ever witness directly. Another puzzle may connect to the same ancient blow, and in some ways it is quieter than the tilt. Uranus gives off very little extra internal heat compared with the other giant planets in the solar system. That alone would be interesting, but the comparison with Neptune makes it especially hard to ignore completely. Neptune is farther from the Sun, receives less sunlight, and yet radiates well over twice what it absorbs. Jupiter and Saturn also emit more energy than sunlight alone can explain, glowing partly from stored formation heat. That is the normal behavior for giant planets, which slowly release leftover warmth from the process that formed them. Uranus, by contrast, seems to radiate only about what it receives from the Sun and little beyond. Its upper atmosphere is therefore extraordinarily cold, colder even than Neptune's despite orbiting closer to sunlight overall. For two planets so similar in size and composition, that difference feels less like trivia and more like biography. Something in Uranus's past appears to have altered the way its internal heat escaped, or failed to escape. One possibility is that the impact simply drove much of that internal heat out long ago in one upheaval. A collision big enough to tip the planet would pour huge energy into it and disrupt the interior deeply. In that chaos, Uranus may have shed a large fraction of its stored warmth early, then cooled afterward. The planet would still be cold today, not because nothing happened, but because too much happened all at once. The other possibility is subtler, and I think it carries its own quiet elegance despite the violence involved. Instead of removing the heat, the collision may have rearranged Uranus into stable layers that trap warmth below. That brings us to convection, which is simply heat transport by churning fluid, rising and sinking through interiors. In a convecting planet, warm material rises, cooler material sinks, and energy moves outward efficiently over time. Jupiter, Saturn, and Neptune seem to manage this well enough to keep leaking substantial internal heat today. If Uranus lost that churning, its warmth could remain imprisoned underneath, while the outer layers stayed strangely cold. Stable layering works because composition matters as much as temperature when fluids try to move through a planet. If deeper material is not only warmer but also heavier in makeup, it may still resist rising upward. That suppresses convection and leaves the interior stratified, like a drink that refuses to stir itself evenly. Heat can still creep outward slowly, but not with the vigor seen in a well-mixed giant planet. So Uranus may contain warmth deep inside even now, hidden beneath layers that do not readily exchange places. The impact in this version did not empty the furnace so much as close the vents above it. I find that possibility especially compelling because it lets the planet remain wounded and sealed at once. It would also help explain why Neptune, so similar in bulk and composition, behaves so differently by comparison. Neptune may simply have avoided the specific rearrangement that left Uranus both tipped over and thermally quiet. The two worlds look like siblings, but one may carry an old interior bruise, the other escaped entirely. This is why the collision explanation remains attractive. It links several odd facts with one early event elegantly. It explains the extreme tilt, offers a route to the aligned moons through a debris disk, and addresses coldness. Science usually prefers that kind of economy when the same cause can account for multiple otherwise separate anomalies. But attractive is not the same as settled, and that distinction matters if we want to stay honest. The simulations are persuasive, the moon geometry is suggestive, and the thermal puzzle fits the same history. Yet none of that amounts to a direct witness, only a very strong case built from converging clues. I think that is part of the beauty here, because the explanation feels sturdy without pretending to finality. Uranus has not handed us a clean confession, only a pattern that points repeatedly toward ancient collision. The pattern may be right in every major respect and still leave important details unresolved beneath the surface. And once those unresolved details come into view, the quieter alternatives begin to matter more than before. And once those unresolved details come into view, the quieter alternatives begin to gather a little more weight tonight. One possibility imagines Uranus once accompanied by a much larger moon than any regular satellite now circling it. A moon like that could tug steadily on the planet's spin across ages, not violently, but with patient insistence. Under the right conditions, that pull could resonate with Uranus's natural wobble and gradually increase the tilt enormously. I find that idea haunting because it replaces one catastrophic instant with something more like a slow persuasion. In this picture, the planet is not knocked sideways all at once, but gently walked there over eons. The missing actor would then have to disappear somehow, perhaps ejected, broken apart, or lost during later upheaval. That vanishing act is the weakness, because elegant explanations become harder once their key evidence no longer remains. Still, gravity can be astonishingly persistent, and the solar system has had more than enough time available. So the lost moon idea stays alive, quiet but credible, in the background of Uranus's long, unresolved history. Another alternative looks beyond Uranus alone and turns toward the early rearrangement of the giant planets themselves. There are good reasons to think those outer worlds did not always occupy the orbits we see today. As they migrated inward and outward, the timing of Uranus's axial wobble may have crossed a powerful resonance. If that happened while surrounding material still lingered nearby, a modest tilt could have been amplified dramatically. The process would be gradual, almost tidal in temperament, but still capable of producing a startling final posture. I like this version because it makes Uranus part of a larger choreography instead of an isolated accident. Yet it also asks for several ingredients to line up properly, which makes the scenario more delicate. A planet, a shifting orbit, a resonance, perhaps a disk or substantial moon, all must cooperate carefully. That does not rule the idea out, but it does mean the path to certainty remains narrow. So the gentler explanations survive, not as fantasies, but as serious alternatives waiting for stronger evidence someday. Neptune helps here because it gives us something rare in astronomy, a nearby comparison that is almost unfairly useful. It formed in the same cold region, from similar materials, and ended up close to Uranus in size. Yet Neptune keeps a far more ordinary tilt, and nothing about its posture suggests a comparable sideways history. That contrast matters because any explanation for Uranus must also explain why its near twin escaped the same fate. A random collision handles that difference neatly, since chance can strike one sibling and miss the other. The slower resonance ideas can still work, but they must explain why Uranus alone entered the necessary circumstances. I always trust comparisons like this because they make mystery feel less abstract and more sharply constrained. Two worlds can resemble each other so closely that their one disagreement begins sounding almost like testimony. Uranus and Neptune seem to offer exactly that kind of paired evidence across the dim outer dark. And even with all this, the best account still feels persuasive rather than final, which is its own kind of beauty. That sense of misalignment deepens once we leave the visible planet and consider its invisible magnetic surroundings. Uranus does generate a magnetic field, as the giant planets generally do, but it behaves in an oddly skewed way. Instead of lining up anywhere near the spin axis, the magnetic axis leans about 59 degrees away from it. That is an enormous separation, far greater than what most people picture when they imagine a planetary compass. The field is not only tilted either, it is also displaced noticeably from the planet's geometric center. So Uranus carries an off-center magnetic field that seems shifted sideways even inside its own internal structure. I think that makes the planet feel almost cubist, as though none of its hidden lines agree. As Uranus rotates, that crooked field swings through space in a lopsided, restless pattern around the planet. The surrounding magnetosphere therefore changes orientation constantly, presenting the solar wind with a moving and awkward target. Even by giant planet standards, it is a strange arrangement, another quiet refusal to line up normally. Researchers think that magnetic oddity probably reflects where the field is being generated inside Uranus itself. On Earth, magnetism comes largely from churning metal deep near the center, which produces a comparatively centered geometry. Uranus seems different, with its field likely arising in a conductive shell of exotic fluid ices instead. That shell may consist of compressed water, ammonia, and related materials behaving nothing like familiar substances here. If magnetism is produced in a thinner, off-center region, the resulting field can become tilted and asymmetrical. So the crooked compass may tell us less about surface appearance and more about hidden interior architecture. I always enjoy when an invisible phenomenon becomes a map of places no camera will ever reach. The field may also create unusual auroras because charged particles are guided into the atmosphere along peculiar routes. But whether the ancient tilting event directly shaped this magnetic geometry remains uncertain and honestly still unproven. It is another clue, perhaps connected to the larger story, yet not one that settles anything by itself. If the magnetic field makes Uranus feel structurally strange, its color makes it feel almost impossibly calm by contrast. Seen from afar, the planet is a soft, pale blue-green, muted rather than vivid, cool rather than dramatic. That color comes mainly from methane high in the atmosphere, which absorbs red wavelengths from incoming sunlight. With the red light reduced, blue and green tones are scattered back outward and dominate what we see. The result is not the deep, saturated blue of Neptune, but something gentler, washed with a faint greenness. I have always thought Uranus looks like sea glass left in winter light, distant and quietly self-contained. A high layer of haze softens the view even more, blurring contrasts and muting whatever weather lies below. That haze helps explain why the planet long seemed almost blank, despite having winds, clouds, and changing seasons. Its face is not empty so much as veiled, which feels appropriate for a world this hard to read. Even the color, then, is part chemistry and part concealment, a surface impression shaped by atmospheric filtering. Beneath that softened face, Uranus keeps a ring system far more understated than Saturn's famous shining architecture. Its rings are narrow, dark, and faint, made of material that reflects very little sunlight back outward. They do not blaze across the sky. They whisper, appearing more like graphite lines than luminous bands. Because the particles tend to stay confined, many of the rings remain remarkably slim instead of spreading broadly. That confinement likely depends on small nearby satellites known as shepherd moons, whose gravity keeps the edges tidy. I love that phrase because it gives the system a pastoral gentleness that the physics fully earns. These little moons do not command the rings dramatically, they simply nudge, restrain, and preserve their narrow lanes. The whole arrangement suits Uranus perfectly, modest in brightness but intricate once you stop rushing past it. And because the planet is tipped so far over, the rings share that same nearly vertical orientation in space. So even here, in something as delicate as ring geometry, the great sideways history keeps quietly showing through. Farther out, the major moons continue that tilted household, each traveling in the same slanted equatorial plane. The five largest are Miranda, Ariel, Umbriel, Titania, and Oberon, names drawn from Shakespeare and related literature. I like that literary naming because it gives the system a faint theatrical quality without making it feel ornate. These moons are not identical worlds repeated 5 times, but distinct icy bodies with their own textures. Titania and Oberon are the largest, older-looking, and heavily marked by impacts and long surface fractures. Umbriel appears darker and more subdued, as though it has spent ages holding onto shadow more faithfully. Ariel looks brighter and somewhat more reworked, with signs that internal activity once reshaped parts of its crust. Together, they make Uranus feel less like a single object and more like a small family in motion. All of them circle a planet lying on its side, and all inherit that unusual geometry completely. Their orderly paths preserve the same message the rings do. This world's odd posture reaches everything nearby. Miranda, though, is the moon that keeps drawing the eye once you linger long enough with Uranus. It is the smallest of the 5 major moons, yet somehow the most visually unruly by far. Its surface looks patched together from incompatible pieces, with terrains changing abruptly as though stitched without smoothing. There are grooved regions, ridges, cliffs, and enormous scarps that seem outsized for such a modest world. Some of those cliffs are among the tallest known anywhere in the solar system, which still surprises me. A small moon is supposed to look simple, and Miranda refuses that expectation with almost cheerful defiance. One possibility is that it was shattered long ago and then reassembled under its own gravity imperfectly. Another is that tidal heating from Uranus stirred its interior and drove resurfacing from within over time. We do not know which account is right, and the truth may involve more than one process. That uncertainty gives Miranda a special charm, like a broken mask whose expression changes with every careful glance. Some of Uranus's moons may also hide something even more intriguing beneath their cold outer shells entirely. Elsewhere in the outer solar system, several icy moons appear to shelter liquid water below frozen crusts. Subsurface oceans are therefore not a wild fantasy here, only an open possibility we cannot yet test. A hidden ocean would require internal warmth, perhaps from radioactive decay, past tidal flexing, or both together. Whether any Uranian moon still has such a buried sea remains unknown, and that unknown feels wonderfully alive. I think possibilities like this make distant systems feel less finished and more quietly expectant than they seem. So by now, Uranus offers us a tilted axis, an off-center magnetic field, veiled weather, muted color, dark rings, shepherd moons, literary satellites, Miranda's impossible cliffs, and the faint chance of unseen oceans below ice. Each clue adds texture, but none closes the case, and that is the important feeling to keep. Because for all this richness, we are still reasoning mostly from a distance, and the closest look came only once. That single close encounter still carries astonishing weight, because nearly everything we know firsthand about Uranus comes from it. One spacecraft swept past on its outward journey, gathered what it could, and kept going into deeper darkness. No orbiter has ever remained there to watch the planet patiently through changing seasons and shifting atmospheric moods. No atmospheric probe has ever dropped through its clouds to sample the air directly as pressures climbed downward. I always find that a little humbling because such a large world has been known mostly by one passing glance. Much of our picture rests on that brief visit, then on decades of careful telescope work from very far away. The foundation is real and scientifically strong, but it is still thinner than for many nearer planets. We have never stayed beside Uranus long enough to let familiarity replace inference and distance with direct observation. In a practical sense, this sideways giant remains one of the least personally visited major worlds we know. That rarity is part of its quiet power, because it still feels partly discovered and partly withheld. The timing of that flyby shaped our first lasting impression more than people often realize when they picture Uranus. The spacecraft arrived near solstice, when one pole leaned strongly sunward and the seasonal geometry favored atmospheric calm. What it saw was a pale, smooth planet with very few visible features and almost no obvious drama. For years, that image encouraged the idea that Uranus was bland, sleepy, and less interesting than its neighbors. I think first impressions in astronomy can linger like weather reports remembered long after the sky has changed. Later observations showed a more active world, with clouds, faint bands, and occasional storms emerging as seasons shifted. The planet itself had not transformed into something new while we were looking away from it afterward. We had simply met it during one of its quieter chapters and mistaken that chapter for the whole story. That feels strangely human to me, though the lesson belongs equally to science and to patience. A single true image can still be incomplete when a world lives on timescales much longer than ours. Reaching Uranus at all is a reminder of just how distant this planet really is from the Sun. It circles at roughly 19 times Earth's distance, where sunlight has thinned into something faint and almost delicate. A spacecraft traveling there must commit to years of motion before the planet grows from point to world. Even then, the close part of the meeting can be heartbreakingly brief compared with the long approach. I sometimes think of outer planet missions as letters that take years to cross a frozen ocean. By the time the message arrives, it has already spent a small lifetime simply getting near its destination. Yet that one flyby still returned extraordinary results despite the shortness of the encounter and the distance involved. It measured the strange magnetic field, refined the planet's rotation, and revealed new rings and moons nearby. It also gave us our only close views of the major satellites, including Miranda's fractured and improbable surface. For a few hours of company, Uranus gave us enough to wonder for decades afterward. And wondering is still the correct posture, because several important questions remain open despite everything already learned. We still cannot say with complete certainty exactly how the Great Tilt happened or precisely when it happened. The leading explanation remains an ancient collision, perhaps one impact or perhaps several early in planetary history. But the exact sequence is still reconstructed from evidence rather than remembered from any direct record itself. I like that distinction because it keeps the mystery honest instead of letting confidence become performance too quickly. We also do not fully know why Uranus releases so little internal heat compared with Neptune beside it. The heat may have been driven out long ago or trapped deep below stable layers that resist mixing. Both ideas fit important parts of the evidence, and neither has yet won the final argument. The coldness is measured, the comparison is striking, and the cause still sits just beyond our reach. That is not failure, only the present boundary line between what has been tested and what remains inferred. The magnetic field keeps another set of unanswered questions quietly turning around the planet with every rotation. We know it is sharply tilted relative to the spin axis and offset from the planet's center. We suspect it forms within a conductive shell of exotic fluid rather than a neatly central deep core. But suspicion is not the same as a detailed map of the interior dynamo at work. I think invisible structures are often the most beautiful mysteries, because they must be known by consequences alone. To understand that field properly, we would need long monitoring from nearby, not a single hurried passage. A visiting spacecraft could watch the magnetosphere swing through full rotations and changing solar conditions over time. Only then could we test how the field behaves, how stable it is, and what drives it. For now, the crooked magnetism remains one more sign that Uranus keeps its internal architecture mostly private. The planet gives us outlines, not complete diagrams, and asks us to live with that difference carefully. Its moons keep their own share of unanswered possibilities, especially where hidden oceans may or may not exist. Several icy moons elsewhere in the outer solar system appear to shelter liquid water under frozen crusts. That makes the same question worth asking here, especially for bodies that may have known internal heating. No observation so far has settled whether any Uranian moon still conceals a dark buried sea. I find that possibility quietly thrilling, because even the coldest systems can hide motion under still surfaces. Miranda also remains unresolved, with its strange patchwork terrain still resisting a single clean explanation today. Was it shattered and reassembled, or reshaped from within by tidal stress and internal upheaval instead? The answer matters not only for Miranda, but for understanding the history of the whole tilted system. Each moon is a small archive, and we have only skimmed a few pages from each one. There may be entire chapters waiting beneath ice, in fractures, or in the geometry of their orbits. Because of all this, space agencies now speak seriously about Uranus as a high-priority future mission target. The appeal is not novelty alone, but the chance to answer several major questions with one sustained effort. A long-duration mission there could do what the old flyby never had time to attempt properly. An orbiter could remain for years, watching the atmosphere, rings, moons, and magnetic field through changing conditions. I think staying is the scientific luxury Uranus has never yet been granted by any human machine. Instead of one fast portrait, we could build a moving record of a world across real time. The spacecraft could track seasonal weather, refine gravity measurements, and test models of the hidden interior. It could also study the moons closely enough to search for signs of internal oceans or recent activity. With patience, an orbiter could begin turning elegant guesses into measurements strong enough to settle old debates. For a planet known mostly by passing, simply remaining nearby would already change the story profoundly. An atmospheric probe would add another layer of understanding that remote sensing alone can never fully replace. Dropped into the planet's upper air, it could sample gases directly as it descended through haze and cloud. It could measure temperature, pressure, winds, and composition at levels no telescope can truly touch from afar. That short fall would end in destruction, of course, as the environment thickened into crushing fluid depths. There is something noble about instruments built for one descent and a few priceless minutes of truth. Paired with an orbiter above, such a probe could connect the visible atmosphere to deeper structure below. Together they could test why Uranus seems thermally quiet and how its chemistry compares with Neptune's. They could also improve our understanding of how ice giants formed, not just this one unusual example. Since planets like Uranus appear common around other stars, learning this world better reaches far beyond itself. A mission there would not simply revisit an old mystery, it would sharpen planetary science across the galaxy. Until that return happens, Uranus remains a place where certainty and wonder have to travel side by side. We know enough to tell a coherent story, but not enough to close every question with confidence. A world was somehow laid nearly flat, and that one fact reshaped its seasons, moons, weather, and interior. The strongest answer is still a great collision near the beginning, tying several oddities into one history. Yet the quieter alternatives have not vanished, and science is wiser when it leaves room for revision. I have always loved that balance, where understanding feels solid without pretending to be final or complete. Uranus is not obscure because it lacks meaning, but because meaning there still arrives in careful installments. Its mystery is disciplined, evidence-based, and patient, which may be the most restful kind of mystery. Nothing about it asks for spectacle, it only asks to be observed well and long enough. For now, the planet continues its sideways turning, whether or not we are ready to explain every detail. And maybe that is the gentlest part of its story, especially at the end of a quiet night. If Uranus was struck long ago, the blow was brief, while the calm afterward has lasted almost forever. The planet did not return to uprightness, and it never needed to in order to keep going. Its seasons adjusted, its moons settled into place, and its long, cold life continued in altered balance. I think there is comfort in that, as long as we leave it simple and let it rest. Not every old disturbance can be undone, and not every changed course must be corrected to endure. Sometimes a world is tipped, and what follows is not ruin, but a different kind of steadiness. So if this journey brought you some peace, a like or subscribe helps this quiet channel keep going. And now you can let the sideways planet drift slowly to the edge of thought and farther. It will remain there, pale and patient, turning in the dark, and you may rest with it.